Hi everybody. For the Carbonates lab, what I want to do is guide you through the first experiment that was done in the lab handout as a guided solution. You don't need to answer this on your own for your lab report, but rather watch me walk through how to solve that problem. What I want you to do is to work through the second and third reaction from the lab handout. So let's go through the first part just as an example problem together. Okay, so the first question says, what's the mass of NaHCO3 in grams before adding HCl? This is our sodium bicarbonate. So let's go ahead and do this really quick. And we can just say, well, in order to do this, what we need to do is we need to take our full beaker, meaning the beaker with the sodium bicarbonate, and subtract the empty beaker. And if you go in the lab handout, you'll see data for this. And it says that the full beaker is 56.273 grams, and the empty beaker is 55.967 grams. And if you plug this into your calculator, you should get 0.306 grams, right? And it's important to kind of label things. I prefer just to kind of keep notes on scratch paper or in my lab notebook, but this is going to be the mass of NaHCO3. It's the mass of my sodium bicarbonate. Perfect. So now part 2 says let's find the mass of the product in grams after drying. So this is the mass at the very end of the residue that was left over in the beaker after drying. Okay, so we'll go ahead and say, well, this is after, and this would be full minus empty again. And the full beaker was going to be 56.171. And then the empty beaker is just going to be the same as it was before, which is 55.967 grams. So if we subtract the two, we're getting 0.204 grams. And the byproduct, or I should say the product of this reaction, is going to be the mass of NaCl. That's sodium chloride, right? This is going to be our product after drying, right? Because in this chemical reaction, we're converting sodium bicarbonate into sodium chloride. Okay, so now we've got question 1 addressed, but we're going to use these numbers that I've boxed in the rest of the parts of this lab report. So let's jump into question 2. Question 2 says, write a balanced chemical reaction for this equation. Okay, but let's kind of piece apart this question. It says depicting solid sodium hydrogen carbonate. This is the same thing as sodium bicarbonate. Okay, so I'm just going to write out the formula, which is NaHCO3. And because it's solid, right? It says solid right here. We need to include the symbol S after it to indicate that it's in its solid state. Okay? And it says we're going to react this with aqueous hydrochloric acid. Okay, so hydrochloric acid is HCl. And to indicate that it's aqueous, we need to put the symbol AQ after it. Hydrochloric acid in its pure form is actually a gas, but in this case, it's telling you that it's in a solution, implying that it's a gas mixed with water, which is kind of interesting. Okay, and what we're going to do is we're going to react this, and then it says we're going to form aqueous sodium chloride, right? So sodium chloride is NaCl, but again, it says aqueous, so I'm going to go ahead and write AQ after here. Sorry, let me keep the colors the same. And then it says that we're going to also form liquid water. So I'm going to go ahead and write water, but then do a cursive L to indicate that it's in the liquid state. It's not steam, it's not ice, nothing like that. And then last but not least, we've got gaseous carbon dioxide. And again, we want to include the symbol G to indicate that it's in the gas state. So let's zoom out a little bit. And I'll just write CO2, that's carbon dioxide. It's a gas, so I'll put in the G right there. Okay, but we're not quite done yet, right? It says write and balance. the chemical reaction. And what balance means is include reaction coefficients, meaning whole numbers, before each of the reagents and products so that we have the correct number of atoms on both sides of the chemical reaction, right? But the weird thing with this is if you go and check, I see that I have one sodium, so that's balanced. I see that I've got 2 hydrogens here, and I've got 2 hydrogens here, so the hydrogens are balanced. I've got 1 carbon here, 1 carbon here, so the carbons are balanced. I've got 3 oxygens here, and then on this side, I've got 1 oxygen and water, and 2 in CO2, so I've got 3 on the right side as well. And then last but not least, I've got 1 chlorine and 1 chlorine. So the reality is, it is balanced the way it's drawn. We don't need to show anything else. We could, if we wanted, write 1 to 1 to 1 to 1 to 1, but we really don't need to show the number 1. So I'm just going to make a note of that. We don't need to show 1s, but it is implied. Or let me just put this in parentheses. It is implied. Okay, so we don't need to show 1s for any of these if they are 1s, right? So we'll just keep that in the back of our head that there's a 1 there. Okay, so question 3 is the tricky one. This is the high point problem worth 4 points. It says using the mass of sodium hydrogen carbonate that you weighed out, calculate the theoretical yield of sodium chloride in grams and show your work. And it says that this is asking about the theoretical yield, not the actual yield, right? The actual yield we actually found up here where it said we actually got this out of the reaction. But what this question is asking is saying, in a perfect world, theoretically, what could you have gotten out? What's the maximum amount of sodium chloride you could have received? And here's some things to consider as you work through the problem. The first one is let's calculate the molar mass of sodium hydrogen carbonate, right? And most of you should be pretty familiar with this. So let's break it apart. To find the molar mass, you need to go to the periodic table and add up the atomic weight of each of the atoms that makes up this molecule, right? So when I look at this, I'm seeing a few things. I'm seeing that I have a sodium atom. Specifically, I have 1 sodium atom. And sodium on the periodic table is 22.99. So 1 times 22.99, it's just going to be 22.99. So not too bad there. Then I go over to hydrogen. I have 1 hydrogen in there. And hydrogen on my periodic table in the textbook is 1.008, excuse me. So I can write this out like this. And then I can go to carbon. Again, I have 1 carbon. And carbon is 12.01. So I could go ahead and write that out. And then oxygen. It's important to remember that I've got 3 oxygens, right? That's what that subscript means. So I'm going to go ahead and write 3 times the atomic weight of oxygen, which is 16.00. If we multiply this together, it's going to be 48.00. And now what we need to do is we need to basically add up all of this, right? So we're going to go ahead and add all of this up, but we need to follow the sig fig rules. And one trick we can do is basically take our least precise number, in this case goes to the hundredths place, and add this all together. But let's just first do it in our calculator. If you do this in your calculator, what you'll find is you'll get 84.008. But the 8 that comes off the end, you see how it's further to the right of the decimal than any of our other values? That means we don't want to include it in our final answer. But it's greater than 5. So according to our sig fig rules, we need to round up. So what I would say is let's change this to 84.01. And what does this tell us? Well, it tells us that there's 84.01 grams of sodium hydrogen carbonate in 1 mole. So let's just go ahead and plug this in. So this is important to include. Okay, so now part B is asking something a little bit different. Part B says, using the mass of sodium hydrogen carbonate that you weighed out, calculate the moles of sodium hydrogen carbonate. Well, in question 1, we actually solved for the mass that we weighed out. That was the full beaker minus the empty beaker. And we said that we started out with 0.306 grams of NaHCO3. But this is asking us to find moles, right? So what I would do is I would set it up as a unit conversion. And I would try to cancel out grams. Let me slide this over a bit. Of sodium hydrogen carbonate. This way, I can cancel out units here and here. But we want to solve for moles, so I'm going to put moles on top. So I'm just going to write moles of NaHCO3. That way, my leftover unit, when I'm all done, is going to be moles of NaHCO3. Okay, but now I need to plug in numbers, right? So the question is, what number goes here and what number goes here? Well, this is where part A comes in. You see how in part A, 84.01 was paired with the grams unit? That means it needs to be paired with the grams unit down here as well. So let's go ahead and plug that number in. I'll say 84.01. Okay, so now I've got 84.1 with the correct unit. I don't want to accidentally put that on top. And then here, I've got 1 with my mole unit. So I'm going to go ahead and plug 1 in up here. And I've got 1 with my mole unit. Everything looks right. Units are canceling. And I'm left with the unit that I want. So what I'm going to do is I'm going to keep all of my sig figs. And then at the very end, we're going to go ahead and look at sig figs. Okay, so let's just spit out the answer from our calculator. So I'm getting 0.003642424, and our units were moles of sodium hydrogen carbonate, or sodium bicarbonate, if you prefer that. I really like including full units with my answer. That way I don't get confused with what I'm measuring, right? So in this case, it's clear that I'm measuring moles of sodium hydrogen carbonate. Okay, so now C says, using the molar ratios, meaning stoichiometric coefficients between sodium hydrogen carbonate and sodium chloride in the balanced chemical equation above, determine the number of moles of NaCl that should have been produced in the reaction. Okay, so here's what I would do. I'm just going to go ahead and I'm going to take this number and use it as my starting point. Okay, so let's go ahead and plug this in. We know that we're working with 0.003642424 moles of NaHCO3, right? So it's saying figure out the number of moles of NaCl. Okay, so this means if we're doing unit conversion, we need to cancel out moles of NaHCO3. That way we cancel out these units here and here. And we're trying to solve for moles of NaCl, so I'm going to put moles of NaCl on top. That way it's my leftover unit. So what it means right here where it says use the molar ratios is it's saying how many moles of each are in the balanced chemical reaction. Well, let's go ahead and check, right? So if I go up and I look at my balanced chemical reaction, it's assumed to be a 1-to-1 ratio, right? We didn't show those ones, but they're implied. So let's go ahead and just plug in the 1-to-1 ratio for this problem. And some of you might be thinking, isn't this kind of silly? Well, kind of, right? It's important to show this, that way our units cancel, because in some chemical reactions, it isn't going to be a 1-to-1 ratio. So we can't always just assume that. So we're going to actually get the same number of moles of sodium chloride as we have moles of sodium hydrogen carbonate. Okay, so we've got this many moles of NaCl. Perfect. Okay, now for part D, it says, let's zoom in a bit, convert the moles of sodium chloride to grams. This predicted amount of product that should form is called the theoretical yield. Okay, so in part C, right here, we already solved for how many moles of sodium chloride we had. Specifically, let's zoom in a bit, got 0.003642424 moles of NaCl. Again, just like with any unit conversion, we want to cancel out our units. So I'm going to put moles of NaCl on the bottom. And what it's asking for is what mass of NaCl will we get. So I want grams of NaCl on top. Okay, so by doing this, we can cancel out moles of NaCl. Perfect. We're left with grams of NaCl. Okay, so in order to do this, we need to find the molar mass of sodium chloride. Oftentimes, the molar mass is the same thing as, or it's analogous to calling something the molecular weight. Okay, I'll just put it like this, that way it's not confusing. So let's try to do this, right? So let's do the molar mass of NaCl over here. So I'm just going to do this kind of in the margins. And when I look at this, I've got sodium, right? And specifically, I have one sodium atom. That one sodium atom is 22.99, which means the mass is just going to be 22.99 here. And then I've got chlorine. Again, I just have one of them. And that one chlorine atom has a mass of 35.45. So we can add these together. In this case, I don't have to worry about sig figs as much, right? Because both of these go to the hundredths place, so we don't have to worry about that at all. But what I would find is we would have 58.44 grams, right? And this would be grams of NaCl per 1 mole of NaCl. So a lot of this should look kind of familiar from our work when we were doing conversions with Avogadro's number and atomic and molecular weights. Okay, so now the question, going back to our initial problem, is what number goes on top here and what number goes on bottom here? Well, down here, we had 58.44 with the grams unit. So I'm going to do the same up here. Let's say 58.44 with the grams unit. And I've got 1 with my mole unit. So I'm going to put 1 on the bottom with my mole unit. That way everything's paired up. So I'm set to go now, right? If I go ahead and I do this, I'm getting 0.212, and I'm going to include all my numbers, 863231 grams of NaCl. Okay, so now we're kind of at the end here. We've gone through part A through D, but we're not done yet. Let's go and assess significant figures here, right? So let's go at the top. So at the top, I've got 4 sig figs, right? Over here, I've got 4 sig figs. Over here, I've got 4 sig figs. Okay, and over here, I also have 4 sig figs. So it looks like the fewest number of sig figs that we have. Oh, sorry, holy smokes. The first one should be 3 sig figs, not 4 sig figs. So if I go through, I should only have 3 sig figs in my final answer, but this number right here is greater than a 5. So what I'm going to do is I'm going to round this up, and I'm going to say our final answer should be 0.213 grams of NaCl. Okay, and this might be confusing some of you. So let me do this a different way. You can actually do this entire conversion in one big long step if you want. So let's start from the beginning and show how to do this using one giant unit conversion. So in the beginning, it said that we started with 0.306 grams of sodium bicarbonate, right? And we said we wanted to cancel out grams of sodium bicarbonate, and in fact, that's what we did in one of our earlier steps. So I'll put grams of NaHCO3 on the bottom, and I'll put moles of NaHCO3 on top. And when we did this, we had 1 mole on top, and we had 84.01 on the bottom. Okay? And then in the next step, we canceled out moles of NaHCO3, so we put that on bottom, and we wanted to get to moles of NaCl. And that's when we said that it was a 1-to-1 ratio. And then in this last step, we said, okay, we've got all of that now. Let's cancel out moles of NaCl by putting it on bottom. And let's get to grams of NaCl. Whoops, I forgot my L there. And we said that it was 58.44 grams per 1 mole. So maybe this will make more sense with sig figs now, right? So over here, we started with 3 sig figs. Over here, we've got 4 sig figs. These ones are absolute ratios, so we don't use sig figs there. And then up here, we've got 4 sig figs. That means that with our final answer, when we're all done, we can put just 0.213 grams of NaCl, because this final answer only has 3 sig figs. So hopefully that makes sense. And when you go to show your work in Canvas, for example, I'm perfectly happy with you showing it as one giant step, meaning show all the conversions stacked up just like I did here. However, if you prefer to kind of show it piecemealed out, kind of like I did with A through D, you're welcome to do that as well. So it's kind of a preference. I know some people feel more confident with unit conversions than others. Okay, so question 4 says calculate your percent yield and show your work. And it says that that's your actual yield divided by your theoretical yield. Well, question 1, way back at the beginning of this video, we said that we actually, from the experiment, got 0.204 grams of NaCl left over after drying. But we just said in the previous question that our theoretical yield, meaning in a perfect world, we should have gotten 0.213 grams of NaCl. So that would be on bottom, multiply it by 100. Our grams are going to cancel, and this is actually going to be unitless. It's just going to be a percent. And it's going to be 95.8%. Again, we started out with 3 sig figs here, and we had 3 sig figs down here. So we want to stick with our sig fig rules and stick with 3 sig figs in our final answer. And what this means is we didn't get 100% of what we were expecting. We only got about 95.8% of what we were expecting. And that leads us to question 5. Consider the percent yield calculated. Was it 100%? Well, in this case, no. Quite clearly, it was below 100%. And then it says, what factors could have contributed to the yield being high or low? Saying I messed up or human error is not sufficient. So you may need to think critically. If you're in lab, what could have happened to have thrown off these numbers? Ideally, this should have been 100%. Why is it potentially a little lower than it should be? Think about common lab mistakes that you could make if you were a student actually performing this lab in person. All right, I hope that helps. Let me know if you have any questions. Also, I've got a separate video for how to show the math tool for Canvas. I prefer that students use the Canvas tool simply because if I have upwards of 96 students uploading separate documents, it takes me a lot longer to grade versus a Canvas quiz. So I would prefer that students use the math tool. But if you are absolutely stuck and the tech's just not working for you, let me know privately, and you can email me your report separately. It just will take me potentially a little longer to grade. All right, good luck studying.